Hello everyone, this is Professor Kuehn. Today we'll be talking about the law of the lever. We are continuing our discussion of Chapter 6 in a student's guide. Let me write down once again what the law of the lever is. So here we might imagine that we have a beam or a lever or a seesaw, and you apply forces to the ends of this, force 1 and force 2, and this is at a distance. It's being applied at a distance L1 from the fulcrum, and this one is being applied at a distance L2 from the fulcrum, and we have equilibrium when F1 is to F2 in the same ratio as L2 is to L1, or the forces bear to one another the ratio of the inverse ratio of the distances to the fulcrum. This is the claim that Galileo is making, and what we'd like to do is prove this, prove that it's true. Okay, and as I mentioned, it can be done experimentally, or this can be done deductively or geometrically. So we're going to pursue the geometrical demonstration, but we're first going to demonstrate it kind of intuitively so you can see where we're going. I think it's always a good idea to try to figure out how one is going to demonstrate this geometrically in an intuitive way before you start jumping into axioms and mathematical derivations. Okay, so once again, we're going to start with a simple axiom. Here's the axiom we're going to start with. He claims that this can be proven. So the law of the lever is true. That is, it can be demonstrated based on a simple axiom, a simple and self-evident axiom. Okay, so what is the axiom we're going to start with? The axiom is that, here it is, here's the axiom. Equal weights at equal distances on a lever will produce equilibrium or balance. Equal weights placed at equal distances from the fulcrum on a lever will produce equilibrium. So in other words, if we had a lever and we had a fulcrum right in the middle, he says it is intuitively obvious that if you press down with the same force on the left and on the right, and if these two distances were the same, that whole thing would still be in equilibrium. It would balance. Okay? And this, Galileo claims, is intuitively obvious. And if you accept this, then we can geometrically demonstrate the law of the lever. So again, starting with that axiom, let's do an intuitive demonstration before we get into the mathematical demonstration. Okay, so how does Galileo do this? Okay, so let's draw a picture like what Galileo does. So imagine that you have a beam that is hanging from the ceiling, and we tie a string right in the middle like this. Okay, now since this bar, if you hang this right in the middle, whatever tendency it has to rotate this way due to that weight, and whatever tendency this one has to rotate this way due to that weight, they're going to balance each other out because there's an equal weight over here and over here. They're at equal distances from the center, and so this thing will be in equilibrium by our axiom. Okay, let's call that suspension point C. So this thing is going to be in equilibrium. Now let's suppose that we were to hang a prism, which is another word for a rectangular block, from this. And let's suppose this rectangular prism was made of wood or stone or some material that the density or the specific gravity is uniform throughout. So this is a nice clean piece of stone with no extra knots or pieces of a different density stone embedded in it. Okay? And if you have this stone that's the same, or this prism, the same length as this beam right here, and if you tie a string onto each side, okay, then this will still be in equilibrium, because once again, remember, this central point right here, you've got the same amount of weight here, and so this whole thing will still be in equilibrium, again, by our axiom. Let's label these points H and I, the end points of this suspension rod, and this stone piece right here. Let me make it so this is our stone piece right here. It could be stone or wood or whatever you want. It's point A, the suspension point, and point B. So he says this is in equilibrium. This is obviously in equilibrium. In equilibrium by our axiom, which is itself obvious. Obviously. I'm having trouble spelling. Okay, obviously. Okay, now what we could do is we could, if we wanted to, instead of hanging the beam like this, let me redraw this. could take that exact same stick where it's suspended at point C and the exact same prism below it. All right. And what we could do is, instead of hanging it from the ends, we could hang it from right here and right here, and from right here and right here. Okay, so just moving these strings in by an equal amount, it's still going to be in equilibrium, right? So that's not going to do anything funny to it, right? So we could do that, and we could then cut this block right in the middle, so we have two separate blocks. So if we move this over halfway, so that this block right here and this block right here are the exact same size, and you move these strings over so that they're right in the middle of this block and right in the middle of this block, nothing should change. This one, we could call that block A, and it has some weight, weight A, and this one is B, weight B. These two weights are the same, of course, and we could move these suspension points over so that this is, we could call this length of A, and we could call this length of B, and still nothing changes. And we can in fact sever, like I said, sever these two blocks, and everything would still be in equilibrium. This whole thing would be in equilibrium because we haven't changed the weight distribution. And moreover, each of these blocks will be balancing now because this string is in the middle of this block, so you have an equal weight here and here. So this individual block isn't going to twist one way or the other, and this block right here isn't going to twist one way or the other. So this is still in equilibrium by axiom 1, or by our axiom, right? Okay, good so far. Now, where does he go from here? He says, let's suppose now, I'll give you a hint of where we're going to go. Let's suppose instead of cutting this right in the middle, you were to cut it a little bit farther to the edge so that this block A is bigger than block B. Okay? And at the same time, you were to move these strings over a little bit. You could do that in such a way that this whole thing is still in equilibrium. Okay, so how would we do this? Let's imagine, I'm going to make a little bit bigger drawing over here. This is still the same setup, but it's just going to be a bigger drawing. Okay, so you've got, once again, this string hanging at point C. You've still got the exact same size block right here underneath it. But if instead of cutting it right in the middle, you were to move the cut over by some distance x. Okay, so you were to move it over, we'll just call it distance x. Maybe it's an inch, maybe it's 3 inches, doesn't matter, we'll just call it x. How far over will you need to move these two strings, these attachment points, in order for this still to be in equilibrium? Well, he says if you're moving this one over by distance x, you're adding an amount of weight to this block, okay? And instead of this string being right in the middle, so we had hung this right here, okay? But you're going to have to move this one over by 1/2 of x for it to be in equilibrium. So this distance right here that you have to move the string over is by a distance x over 2. Why do you have to do that? Well, because you still want this string to be in the middle of this block, so you have equal weights on this side and this side. And if you added a length x to this block, you're adding extra weight. You need that extra weight to be distributed equally on both sides of this string. So you need to move this one over by distance x over 2. Likewise, if this one had been in the middle, right, equidistant there, you need to move this one over by the same distance x over 2, because you're taking away x of weight from this one, so you need to move that over by x over 2 in order for this block right here to be distributed evenly on the right and left sides of that string, right? So there's a relationship between the extra size of the block you have over here, or rather the extra weight you've put on over here, and how far you have to move these strings over, okay? And if you do this, you can still maintain equilibrium. And what Galileo's proof that we're going to do in our next lecture is basically a mathematical version of this intuitive demonstration I've shown you right here. So again, if you move this cut over so this block weighs more, you've got to move this over by a prescribed distance related to how much extra weight you add on. And likewise, when you took weight away from this one, you've got to move this over by an amount to compensate so that this one is still in equilibrium. And so there's going to be a new ratio of these 2 points at which you're applying these forces. So we could call this length A and length B, these new lengths. And this block is a new weight, weight A and weight B. And he's going to argue that this weight is to this weight in the inverse ratio of this length to this length, which is exactly what the law of the lever is. Okay, so that's where we're going with this. Let me draw one more drawing just to give you, just to provide one more highlight to this. So notice that when this thing is hanging and this thing is hanging, this doesn't really depend on them being rectangles. You could have, once you have this thing all balancing the way that it is, you could replace this rectangular block with any shape block as long as it's got the same weight and the same distance here. So you could have the suspension point be at LA and replace that rectangular block with just maybe a big spherical weight, as long as it's got the same weight as that block. And likewise, you could replace this little rectangular block, if you're going to have it at length LB, with another weight that's a smaller weight, as long as that new weight is the same weight as that right there. Okay, so this doesn't critically, although he used this rectangular prism in the demonstration, in the end it doesn't matter what shape these are. And he's going to say that the weight A is to weight B in the inverse ratio of the lengths. LB is to LA. And that is the law of the lever. And again, we haven't proven it geometrically, we've proven it kind of intuitively by argument. Okay. Next lecture, we're going to prove this geometrically a little more tightly, so you might want to review how to do geometrical proofs in the meantime.